These videos are offered on a pay-what-you-like basis. You can pay for the use of the videos at my website. There is a link to my website in the info box. The address is www.freelance-teacher.com/videos.htm, or you can just use the link in the info box. By the way, I also offer tutoring via Skype, and you can find more information about that Skype tutoring service at my website. Thanks. What's the name of this molecule?
Benzene.
Right. Now, I guess we could also call it 1,3,5-cyclohexatriene or something like that. However, it's not called that. And the reason is because this has special properties that you wouldn't normally expect. So it's not just called a cyclohexatriene. It's given a special name because it has special properties which are covered under the idea that it's aromatic. This is an aromatic compound. Does that mean that benzene is happy or unhappy?
Happy.
Happy. Nature likes having aromatic compounds. This is a happy and stable compound. That doesn't mean that we might not possibly lose the aromaticity, but what it does mean is that if we lose the aromaticity, nature's going to get it back. In fact, I think that's going to be universal for these chapters. Anytime we lose the aromaticity, we're always going to get it back. We saw something a little bit similar to that with carbonyls. We know that nature likes carbonyls, so anytime you have a nucleophilic attack that unforms a carbonyl, nature likes to try to reform the carbonyl. We saw that sometimes, like when you're attacking an aldehyde or a ketone, there's no way to reform the carbonyl. But for carboxylic acids and acid derivatives, anytime you attack the carbonyl, you try to reform the carbonyl. Well, with benzene, we're only going to look at reactions where we can always reform the aromaticity. Now, would we expect the carbon-carbon pi bond to be nucleophilic or electrophilic?
Nucleophilic.
Nucleophilic. We learned that last term when we were looking at electrophilic additions to alkenes. Carbon-carbon pi bonds tend to be nucleophilic, which means this should be at the tail of the arrow. So who should this get attacked by? An electrophile. Before we actually go through this mechanism, I should mention one other thing. How many other things are attached to this carbon?
One.
Yeah. And in fact, there's a hidden hydrogen on each of these carbons. It's easy to forget that. In a normal benzene, there's exactly one hidden hydrogen on each carbon, but no more than that, because that would exceed the octet rule. So we shouldn't forget about the hidden hydrogen on each carbon, even though we don't usually draw it in. Now, if this electrophile attacks, if the electrophile attaches to this top carbon, that would leave a positive charge on this bottom carbon. Or you could equally well have said that the electrophile attaches to the bottom carbon and then there's a positive charge on the top carbon.
Is this reversible?
This reaction right here? Usually not. Usually this is not reversible. Now, what's going to happen now?
The conjugate base is going to steal a hydrogen from where the electrophile is attached and remake the double bond to make it aromatic.
Very good. That's very good. Sometimes students think that, so now there's two things attached to this carbon. Remember that what we want to do is get back to aromaticity. Well, how can we get back to aromaticity? By restoring only one thing to being on this carbon. So we have to lose this hydrogen, and that frees up the electrons here to restore this bond. Who's going to take the hydrogen? Well, that depends on the specific conditions. Depending on what type of electrophile we're using, that will determine who's around to take this proton. So I'm not going to show who's going to take the proton, but there will be someone around to take the proton. And that would get us back to here. And as I said, we've reformed the aromaticity. Remember that when we were attacking carboxylic acids and acid derivatives, the basic steps were attack the carbonyl, reform the carbonyl. But this is actually a very similar mechanism. This is a mechanism of unform the aromaticity and then reform the aromaticity. And that's what we're going to go through in each of these reactions. What's the name of this mechanism?
Electrophilic aromatic substitution.
Electrophilic aromatic substitution. Why is it called electrophilic? Because it's an electrophile that attacks the benzene. Why is it called aromatic? Because the benzene is aromatic. And why is it called substitution?
Because you're substituting the H for electrophile.
We're substituting the electrophile for the hydrogen. That's right. It's easy to forget that because we didn't draw the hydrogen in this picture. But there used to be a hydrogen on this carbon. And now there's this new electrophile. So this is overall a substitution. It's good not to forget that there's hidden hydrogens on these carbons. A lot of people just think of this as like gluing the electrophile on. But in order to glue it on, we have to kick off this hydrogen. Let me point out another mistake that people oftentimes make. Sometimes people think that we're going to lose this hydrogen. But this is not the hydrogen we need to lose. We need to lose the hydrogen where the electrophile is, so we can get back to having only one substituent over here. So that's a mistake people commonly make in this mechanism. That's our electrophilic aromatic substitution reaction. And now what was chapter 15 about? Chapter 15 was basically just about learning all the different types of electrophiles that you can add to the benzene. And it sounds like you guys actually feel pretty comfortable with that already, so we'll just survey those so we can go on. Now, this is a trick question. What's going to be the product of this reaction?
No reaction.
That's right, no reaction. What do we need to add to get a reaction here?
Some sort of
FeVr3.
yeah.
What type of molecule is this? This is what's called a Lewis acid. It's called a Lewis acid. There's some other Lewis acids you might use as well, but FeVr3 is a common Lewis acid that's used here. Now, we shouldn't be surprised that we need a catalyst, because remember, the benzene is so happy that it's going to be hard to accomplish that first step. Remember in the last term we talked about the idea of the rate determining step, or the hard step. That's what determines the reaction. Like, the rate determining step in SN1 is when you form the carbocation. That's hard. It's easy then for the nucleophile to attack and get rid of the carbocation. Well, which is the hard step in electrophilic aromatic substitution? Unforming the aromaticity or reforming the aromaticity. Obviously, unforming the aromaticity is difficult. Well, this catalyst here can help us with that first step. Basically, what we need is something that will make this a better electrophile. Well, how do we make something a better electrophile? With an acid or a base?
Acid.
Yeah, acids make things into better electrophiles by giving them positive charges. This is a Lewis acid. In the past, we've usually used Bronsted-Lowry acids that donated protons. Here we're going to use a Lewis acid that just donates electrons, but either way that can make this into a better electrophile. So we need a catalyst for this halogenation reaction. Incidentally, well, we'll come back to that. FeVr3. Okay, now actually what I was planning to do here was to go through all the mechanisms from chapter 15. But actually, since you guys want to cover as much of chapter 16 as possible, maybe we'll leave out the mechanisms, since it sounds like you're kind of comfortable with those.
They're in the book, right?
Yeah, they're in the book. And actually, even though you should know the mechanisms, for most problems, it's best just to draw the product without the full mechanism. So let's just draw what the product would be here without going through the whole mechanism.
And all the mechanisms for these kinds are almost the same, right?
Well, there are some little difficulties because you have to show how we're interacting with the Lewis acid. So there are some...
quickly, just...
Sure. Okay, so quickly.
Rather be safe than sorry.
Right. We do this. Let's draw what we would get from this step. Good. That's very good. The thing that you guys both did well there is you got the charges right. That's what most people get wrong here. This is starting neutral and losing electrons, so it should be positive. And this is starting neutral.
And gaining electrons, so it's negative, yeah.
So it should end up negative. By the way, I said earlier that a Lewis acid donates electrons, but I misspoke. I should have said that a Lewis acid receives electrons. That's what's putting the positive charge here. By receiving the electrons, it's putting a positive charge here. Well, you can see that this has made these bromines more electrophilic. Positive charges make you more electrophilic. Well, now let's show the mechanism for the next step. You got